Today's talk is about how we can go forward with quantum optimization, how to benchmark any algorithm, and for an industry, from an industry perspective. So all the results here were developed within our public funded project based on insights that we acquired there. So what we did was a lot of annealing. We started 3 years ago and modeled our problems for annealing, for the D-wave hybrid solver, or use Quora. And for the hybrid solutions or hybrid solver, we could actually solve industrial relevant problems, but we couldn't tell how much quantum played a role there, if it's scalable. And for the other solution methods, just pure annealing or Quora, we can't just tell anything. So then we had the idea, for hybrid, or we saw hybrid benchmarking, which could be a solution. So let's use this working hypothesis that the optimization problems we want to solve in industry are NP-hard. There are exceptions, but most likely the problems you will encounter are NP-hard, which is most of the time quite trivial to see because they are just generalization of well-known NP-hard problems. The consequences are both classical and quantum that we won't be able to solve them probably in polynomial time. For classical solution methods, so exact algorithm, meaning they have a proof that they will terminate with an exact or optimal solution, we have a worst case exponential runtime. And here's the case, worst case, you don't need to experience that in reality, but normally you have that. So in industry or in application, you use heuristic or iterative approaches. So if you have a MIP solver, it iteratively finds new solutions. When you look at the Gobilog, it gets better solutions during the process, and you typically stop them before they prove optimality. And so it's basically used as a heuristic because you can prove that after, let's say, 10 minutes, you will have an optimal solution. Or if this even doesn't work, you have heuristics, special purpose algorithms you implement to solve those problems. Again, for quantum, we cannot hope for exponential speed up. And now it's important that exact and pure quantum algorithms, which are like one circuit you run and measure at the end, the best case is exponential runtime because you always take the same time to run that circuit. So we need quantum circuits or quantum algorithms which grow polynomial in the input size, so polynomial number of gates. The consequence is that we need heuristics, preferably iterative approaches, because we can't have exact quantum algorithms. And their performance is determined by benchmarking and through experience. And it's not only a problem because nobody likes to do those benchmarks and experience, but also because, we have two possibilities. You can put it on quantum hardware. It's too noisy. You won't get any kind of good results out of it. Or we have simulation. Simulation is just too small. You can't do much with it. So the idea is use hybrid benchmarking, which is basically estimating the runtime via gate counting, which we heard from Nikolai from Boehringer, who did that, and compute or estimate compute the solution quality just with classical method. And classical method is not simulate the circuit, but any kind of other method, like using Gurobi, for example, which is able to solve problems with hundreds of binary variables within seconds, whereas you cannot simulate such a circuit. The consequence is that your quantum algorithm must be exact. So it has a proven solution, so you can reproduce a result with the classical method, which will then probably run an exponential time or doesn't have an exponential speed up. And for those methods, there's a small regime where you can have exponential speed up. For example, if you somehow want to factorize numbers, or normally you have probably a quadratic speed up, or some kind of polynomial speed up. And the consequence from that is that the quantum algorithm must be a subroutine in some bigger hybrid setting, because otherwise we cannot have an exact algorithm. And for example, if we want to compute the runtime, we start with the circuit at the left, which is from a stat clause. It turns the third qubit on if this clause is not, or is not satisfied. So the first one would be a true, and the second a negative literal. We transpile it. I chose 3 different kind of rotation gates, and the C0 gate gets longer. Based on that transpiled circuit, we can compute the computational graph, assign to each of the gates execution speed, and compute the longest path, and estimate the runtime of this circuit. This assumes that you can execute your gates in parallel, if possible, and for very slow gate execution times, it's probably valid. If you have very fast execution times, it's probably not valid anymore, this assumption. So for a hybrid scheme, could look like that. So you have a classical preprocessing, then you have this routine which iteratively calls in your quantum routine, and then you have a post-processing. The solution quality is just computed by running the classical part. You get a solution, you know the solution quality. And the runtime is you track or you log the starting point of the classical proxy method and replace it by the runtime, the estimated runtime of your quantum routine. And at the end, you have a solution quality, which you can compare to other methods, and you have the runtime estimated through this gate counting. And an interesting use case or is the quantum simplex algorithm, which solves linear programs. Preprocessing would be to reduce the number of variables, reduce the number of constraints. The classical subroutine geometrically starts at some point of your polytope and goes from edge to from vertex to vertex until it finds the optimal solution. And algebraically, at each iteration you find a new variable which enters the basis, and this computation of which variable enters the basis, which leaves the basis, can be replaced by a quantum algorithm or quantum method, which has some kind of polynomial speed up. Also interestingly, the simplex algorithm can solve NP complete problems, deciding which or if one variable enters the basis is NP complete. So and this was already done for the simplex algorithm. And here we can see the benchmarking, and the authors computed the required execution time of each of the gates. So they said each gate takes the same amount of time. They counted the gates and computed how fast they have to be, such that you get a speed up. At the top we can see the current speed record. It's I think 6.5 times 10 to the minus 9 seconds, and for those easy problems we have 10 to the minus 16, maybe 10 to the minus 14, 15 execution time, so you have to be much faster than it's currently possible. And easy here means that the quantum simplex algorithms, the runtime depends on the sparsity of your problem, and the sparser the problem is, these are the easy problems which come from graph problems. Green. We also tested that on the SAT problem. So what we did, we just took the easiest algorithm there is, Grover, and the easiest problem there is, it's the satisfiability problem. So you can actually implement that very fast and get some kind of solutions and see where we have problems or what we have to solve doing that. And the MIP, the SAT problem was defined or formulated as a binary linear program. Why? Because this is what we are interested in. How fast can Groby solve it compared to our quantum methods or classical quantum methods? Because in industry, it's always the easiest way to formulate your problems or just formulate the problems as a binary program or like linear program. Because every time you talk to the business, they say, we need to add something there. This requirement needs to be included, and then you just have to either add a constraint or new variables, but you don't have to re-implement your solution method. Yeah, what we learned, not only theoretically, also practically, transpilation is quite hard. It's very slow. It took forever to transpile our circuits, and we did for the SAT problem each clause by clause. So we didn't construct a whole big circuit. We did clause by clause. So there could be more potential for optimization, but we couldn't use that. It sometimes didn't work, and there it was really nice that we had a very easy problem, because when Qiskit doesn't transpile or compile your circuit, you don't know, did you implement something wrong, or was it transpilation? And for a controlled NOT gate, which a lot of control qubits, it's very easy to implement, and it's going to be Qiskit who has problems with it. We had to do a lot by hand. For example, the Grover diffuser, we just computed the number of gates we needed, more or less by a formula by hand, which works here, but it wouldn't work if you really want to solve the problem on a quantum computer. You cannot compute it by hand. Yeah, so a lot of things have to be done manually. And here we can see that for our problem, we didn't know the number of solutions. So there's at least one solution, because we knew that the instances were satisfiable. And we can see for the best or for the smallest instance, we need a gate execution time of 10 to the minus 35, which is quite slow. On the other hand, if we would have 100 solutions, we need the execution time, which is lower than the best known so far, which you can see by the green dots. And for real-world use cases, we definitely need to use a pre-solve. We didn't do that here, so we have to reduce the number of parameters, numbers of variables, one number of constraints. And those pre-solving also are very important in classical methods. They always work, so we should use them there. An interesting application would be binary quadratic constraint programming, because on the theory side, they have the same worst-case runtime than linear binary programs. In practical, they are much harder to solve. They take much longer. And another thing that, for example, mixed integer linear programs would be very complex to implement. You have to look how to add integer numbers, how to solve or implement a solution of a linear system of equations. Yeah. Another application could be the DQI algorithm. The problem is that you solve a Maxwell-SAT problem. You have, let's see if I can point. Yeah, more or less the system of, let's call them equations, but you don't have an equality sign, you have an element sign of this FE. If you choose your prime number big enough, so this must be capital, and you have an equality sign here, you have a system of linear equations with integer solutions. And for that, the DQI gives you an approximation ratio. So depending on some kind of decoding quality, mu, you can say that the fraction of satisfied constraints is given by this nice formula. Independent of r, it's bigger than this mu. And for small r, for example, if you have a system of linear equations, this r would be 1, so the smallest possible. If you want to put everything in there, you can choose p big enough, and then you get basically this decoding quality, which also means that the complexity of this problem is moved to the decoder, which might help, which might, or might not. And how you can compute the solution quality is replace this DQI by a MIP solver. And you take the probability that a constraint is fulfilled, and if it's fulfilled, you leave it in your problem formulation. If it's not fulfilled, you just leave it out. And then you solve the MIP with just the selected constraints, and you can interpret your solution quality and say something about it. We assume that the constraints are fulfilled independently of each other, which is not really valid, but it's a starting point, because what you can have the same constraints twice, and if one constraint is fulfilled, then the second copy of it will be fulfilled as well, or the other way around. And for the decoder, we probably need a heuristic, because otherwise we run into the complexity theory stuff again. You can determine the quality of the decoder experimentally. Yeah, and the complexity is moved there. And the runtime is computed as by counting your gates and assigning a run execution times to it. It's probably quite complicated to implement your classical decoder, which you created into a quantum fashion. But in theory, it's possible. One application could be this multi-knapsack problem, where you assign, for example, jobs to factories, and the factories have a certain capacity. And in our version right here, we say that each job must be scheduled, and you can easily reformulate that into this Max-Lin-Sat problem. So small or equal means it must be between 0 and this capacity. Job constraints, each job must be scheduled, and we have binary variables. So right here in the Max-Lin-Sat, it could be from 0 to some kind of prime number p, and we can have an interpretation of a not feasible solution. So violated constraints, for example, if we violate our resource constraint, we just deselect jobs to a factory. If a job is not scheduled at all, it's just a suboptimal solution. And if your binary variables are bigger than 1, you just reduce it to 1, which should have no influence on this constraint. We also tested that on the Max-Sat problem. Again, this is just a proxy for binary linear program. It was quite fast to implement. We have that there is an approximation factor of 0.77. So if you have a decoding quality above this factor, you have an exponential speed up. In our experiments, we could see that we need a very good decoder, because after approximately 100 seconds, we have 99.9% of our constraints were fulfilled for this instance, and almost 100% for the other instance. This instance was solved to optimality at the end. Instance 2, I couldn't solve for optimality within 4 days of running Gurobi. And this shows you need practically very good decoder. Also, the experiment showed that the original Sat problem was way easier to solve. So those problems which wouldn't be able to solve within 3 days were a few seconds if you formulated a Sat problem, not a Max-Sat problem. Then the question rises, what problems should be solved? So normally those MIP solvers, they're quite good if you have more constraints in them, because they can reduce the search tree quite well. If you don't have those constraints inside, or you have them at the optimization, they cannot reduce the search tree. So 3 takeaways is we can benchmark quantum algorithm without quantum computers, or estimate the runtimes. For that, the algorithm must be exact, so you have a proven solution. You know which solution comes out. You can recompute them with a classical computer or classical algorithm. And those exact quantum algorithms must be part of a quantum classical solution methods. Otherwise, you run into the problem with complexity theory. That's it. Any questions?